All right, so here's some familiar applications of differentiation, but these will involve a function that has an exponential in it, and we're going to determine the relative extrema of this function. Also, I think we should do concavity, which I forgot. So also we'll determine points of inflection. So first we'll focus on the relative extrema. Well, let's find the derivative first. The derivative of this function, you have to use a product rule here. So it would be first times the derivative of e to the negative x. So remember, the derivative of e to the negative x would be e to the negative x. That doesn't change, but then times the derivative of the exponent, which would be -1. So let's just do that. So that's the first times the derivative of the second. Now plus the second times the derivative of the first. Second is e to the negative x times the derivative of the first, which is 1. So we're done. To find the critical numbers, we're going to factor that. But before we do, let's find the second derivative, since we're also looking for points of inflection. So the first part of this is going to be very similar to what we just did. It's a product rule. The only difference is we have negative. So really, if you think of the negative factoring out, that the derivative of this is going to be exactly this, but with a negative. So what I've underlined is going to be positive x e to the negative x minus e to the negative x, because it's the exact same thing as this, except with a negative in front of it that we can factor out. So I just use this answer and apply the negatives. Now we also have to, since we only did this one, we also have to now take the derivative of e to the negative x. So it'd be plus e to the negative x times -1 again, so minus e to the negative x. Well, now we have a like term here, so we have two of them. So there's your second derivative. So now I'm going to start finding everything. First of all, the critical numbers. I'll factor out e to the negative x. And find out where this equals 0 is undefined. Now, an exponential function will never equal 0. Just think about it. The one guess would be, well, what if x is 0? Well, that would be e to the -0, which is just 1. So you know what exponential functions look like. They never cross the x-axis, so they're never 0. So the only critical number is where -x plus 1 would equal 0, or x equals 1. We need to find out where that's a minimum or maximum. So you can set up your chart. Let's do that. Exponential functions are defined for everything. So this is going from -infinity to +infinity. So the derivative at 0 is e to the negative x is always positive. Your exponents will always be positive. And -0 plus 1 is positive, so this is positive. If you plug in now, say 10, you get a positive, because it's an exponent, times a negative, which is negative. So it goes from increasing to decreasing, therefore it's a maximum. Probably would have been easier, since we had the second derivative, though, to use the second derivative test to find a min or max. So just as a quick review, the second derivative test if you plug in this critical number, x equals 1, you get e to the negative 1, which is a positive, minus 2e to the negative 1. Well, we can add those together. That's negative 1e to the negative 1, which is a negative number. So that indicates with the second derivative test that that's concave down, so that's a max. So both tests reveal that we have a maximum at 1, comma. Plug in 1 into this original function here. You'll get 1 times e to the negative 1, or just e to the negative 1, or 1 over e. So we're done with the relative extrema. Let's look for points of inflection. That should be pretty easy since we have the second derivative calculated. So I'm going to translate this down here and factor it. So the second derivative simplifies into e to the negative x times the quantity x minus 2. That tells us we have a possible point of inflection at x equals 2. So we're going to set up our chart like we did using the first derivative test, and now we're going to use the second derivative instead to see if it changes concavity. So if you plug 0 into this second derivative, you'll get a positive number because it's an exponent times a negative number. So that means it's concave down on the interval negative infinity to 2. If you plug in 10, you'll get e to the negative 10, which is positive, times 10 minus 2, which is positive. So it goes concave up. Since it changes concavity, 2 is a point of inflection. And we just have to plug in 2 to find the y-coordinate. Remember, plug in 2 to the original function. And that would be 2 times e to the negative 2. Since e to the negative 2 is 1 over e to the positive 2, then this is our point of inflection. So that's what that's hopefully those are right. Hopefully is a good word. Just graph the original function and see if it makes sense. So that's what the graph looks like. It looks like it has a max at 1. I'm going to just quickly calculate the maximum from 0 to 3. So it says 1, 0.367. So 1 point, hopefully 1 over e is about 0.367. But that's like 1 over 2.7, so that makes sense. It says there's a there's a point of inflection at 2. So let's just look at the value. Second calc value at 2. So it draws us our little x here. That x looks like it goes from concave down to concave up, which is true. And then it's at 2, 0.27, which is 2 over 9-ish, because e is 2.7, so that also makes sense. So there you go. That's a good application problem. At least I think so.